Welcome back everyone. In this lesson we are going to learn about multiple roots. From the previous few lessons we have seen that using the bracketing methods and open methods we can find out one root at one point. But it might happen that your function has multiple roots. So how we are going to approach these scenarios, and that is the discussion of this lesson. So let's dive into the details of these multiple root finding approaches. So let's look at our first scenario where we might have two similar roots. Look at this function f of x equal to x minus 3 multiplied by x minus 1 multiplied by x minus 1. So it is very much prominent that there are two similar roots, x equal to 1. That means at x equal to 1 there will be two roots. But the problem is that how we are going to find out that this root is multiple root location. That means if we are using the open methods or bracketing methods, we are going to find this location x equal to 1. But how do we interpret that whether this location contains one root or two root or multiple roots? That's the question here. So if you remember from the discussion of the few lessons before, that whenever a function touches the independent axis, that means the x-axis, there will be multiple roots at that point. So from the graphical approach, from this graphical curve, if we see that the function touches the x-axis at x equal to 1, so this is the condition for having multiple roots. So whenever a function touches any curve but does not cross it, then there are multiple roots at that point. So in our case at x equal to 1, since the curve is tangent to the x-axis, that means we are going to have multiple roots. So since this is a function having two similar roots, that means at that point we are going to find out two similar roots. So this is the first scenario. Let's look at another scenario. In this case, we are going to find out that our function has three similar roots. Look at this. At this point, x equal to 1, now we have three similar roots. But what is the difference from the previous slide? In the double roots, we saw that our function touches the x-axis but does not cross it. But in this case we have three similar roots. So also at x equal to 1, our curve is tangent to the x-axis but do not cross at the x equal to 1 point. Rather it crosses the x equal to 1 point at a slightly further point from x equal to 1, and that's the difference. That whenever we have two similar roots, our function does not cross the x-axis, but when we have three similar roots, our function is going to cross the x-axis, but our function is going to touch the x-axis at the specific point x equal to 1. So that's the very difference between double roots and triple roots. So there is a general formula that whenever we have odd multiple roots, that means 3 roots, 5 roots or 7 similar roots, then the function is going to cross the axis. But whenever we have even multiple roots, that means 2 roots, 4 roots or 6 roots, our function is not going to cross the axis, rather it's just going to stay on the same side. It's just going to touch the x-axis. So that's the difference between odd multiple roots and even multiple roots. So let's look at another scenario where we have 4 similar roots. At x equal to 1, we have 4 similar roots. So the function, since this is a case of even multiple roots, since our multiple roots are 4, so that means our function is not going to cross the x-axis at x equal to 1. As a result, look at this figure. Our function is just touching the x-axis, not crossing the x-axis. So that's the difference between odd multiple roots and even multiple roots. But the question is, even with the double root, our function touched the x-axis, and in the quadruple roots our function is also touching the x-axis. So how do we are going to interpret this result, whether this point contains 2 roots or 4 roots? That's the question. That's the main problem here for multiple roots. So there are some approaches and tricks that we are going to follow. For example, in the case of even multiple roots, that means whenever we have roots of 2 roots or 4 roots or 6 or 8, that means even multiple roots, we are not going to use any bracketing method, because in the bracketing method the condition was that at the vicinity of the root we are going to assume a boundary, and within that boundary there is going to be one root, and the function value at the two boundary locations will be different. But in case of multiple even roots, since our function stays at the same side, that means our bracketing methods are not going to work, and that's why this is the approach that we are not using the bracketing methods in case of even multiple roots. But for odd multiple roots we can use the bracketing method, since at the odd multiple cases the function crosses the x-axis at the root, and that's why our bracketing methods are going to work there. So that's the caution that we are going to use. So in case of even multiple roots we are just limited to the open methods only. But there is another crucial problem. For example, we are using a even multiple scenario. That means we are going to use the open methods. So even using open methods, there are some problems that we might face. So among the open methods, there are Newton-Raphson method and second method. And if you remember, we need to calculate the derivative of the function f prime of x whenever we use these two methods. That means Newton-Raphson method and second method. But in case of multiple roots, at the point of root, at the exact point of the root, the function is going to touch the x-axis in case of even multiple scenarios. So as a result, the function is just tangent to the x-axis at the root, at the specific point. That means at that specific root point our function has the slope of 0. That means whenever we are approaching the true location of the root using Newton-Raphson or second method, the slope of the function is going to approach 0. And it might happen that at the very close point of the root, the derivative of the function is going to be exactly 0, and it might happen at some cases. As a result, the derivative of the function is going to be very small, and the whole value of the function is going to be very large for Newton-Raphson or second method formulas, because in those formulas the f prime of x is in the denominator of the formula. As a result, if f prime of x goes to very small, the function value is going to be very high. As a result, it might happen that the problem that we are going to face, that the function derivative value is going to be 0. And that's why in the code, in our MATLAB code or Python code, we are going to check that whether the f prime of x or the derivative value is lower than a predefined small value. If the predefined small value is set to very small, our program is going to terminate whenever the derivative of the function is going to be less than that predefined value. So that's the remedy of the using the open methods. In some cases there are some problems of using open methods also, so we are going to be careful about that. So there is another problem of multiple roots. If you remember the Newton-Raphson method and the second methods, both of them converge linearly to the root of the function. As a result, they are not converging quadratically. So there is a remedy of this problem. Ralston and Robin Wirtz, they have formulated a new function for the Newton-Raphson method, which is a modified Newton-Raphson formula, where we are seeing that xi plus 1, the new approximation of the root, is determined from xi minus m multiplied by f of xi divided by f prime of xi. So they incorporated a new term m. M is the multiplicity of the root. For the double root, the value of m is 2. For triple root, the value of m is 3. For quadruple root, the value of m is 4. So m is the multiplicity of the root. That as a result, the Whenever our function has multiple roots, whether it is double root or triple root or quadruple root, the value of m is going to change accordingly. That means the function is no longer a linearly convergent function, rather it's either quadratically or higher order terms. So as a result, this function is more suitable for higher multiple order roots, this modified function. But the problem is that we are going to be sure that we are using the correct value of the m. That means we need to have any kind of knowledge about the multiplicity of the root before the method. That means before applying the method, we must know the value of m. That means we must know the multiplicity of the root. That's one problem of this approach. But if we know the value of the multiplicity, then it's going to be very easy. So that's a very handy approach. But there is an alternative remedy for this approach, which is remedy 2 here we are using here. Ralston and Robinowitz, they also expressed that in 1978 a new function u of x, that is the ratio of the function and its derivative u of x, they define this new kind of function f of x divided by f prime of x. So in this case, what we are using, that the u of x can be used as an alternative remedial of the previous remedy. U of x has roots at all the same locations at the original function f of x. So if we are saying that u of x is a separate function, it's not. Rather, what we are preserving here, that all the root locations of f of x are very much similar to all the root locations of u of x. So this u of x, if we replace the function value f of x by f prime of x using u of x, that is not going to harm our method. So if we substitute this, xi plus 1 equal to xi minus u of xi divided by u prime of xi. This u function is denoted something like that we seen, u of xi is f of xi divided by f prime of xi. So that is the new function that we are going to replace in the main function. The benefit is that we are not using any parameter m. As a result, there is no need of foreknowledge about the multiplicity of the function. So that's one remedial of the multiple roots problem. So if you find out the value of u prime of xi, remember u of xi itself is denoted as f of xi divided by f prime of xi. So if we are going to use a u prime of xi, then we are going to differentiate the whole term f of xi by f prime of xi. So if we calculate the whole term, we are going to find out u prime of xi something like this, u prime of xi. So it incorporates both first order differential term and second order differential term. So if we substitute this u prime of xi and the value of u of xi into this equation, we are going to find out our modified Newton-Raphson formula. In this formula, we need to use both first order differential term and second order differential term. So this is our modified Newton-Raphson formula for the multiple roots. So using this formula, we can easily converge to the root location, but still there are some problems that we are not ensuring whether this new root location contains double roots or multiple roots or triple roots or quadruple roots. We do not know that. So but using this formula, our function is going to be very much faster than using the traditional Newton-Raphson formula. Similarly, we can derive a modified second method for this multiple root version, but that we are not going to specify in this lesson. That is your homework. You are going to derive the multiple root version of the second method. This is the multiple root version of the Newton-Raphson method. Then your task is to derive the multiple root version of the second method. Let's look at some of the cases where we might encounter nonlinear equations. nonlinear equations are of the form of something like this, equation 1. So where all the terms, say a terms and b terms, are constants. So this is a linear equation. I'm sorry, this is a linear equation. Equation 1 is a linear equation. So any kind of equation that does not fit this form of equation, then they are nonlinear equation. For example, look at this x square plus x dot y plus 10 equal to 0. This function is a non-linear algebraic equation. Why? Because we cannot fit this function in the form of equation 1, and that's why it is a non-linear algebraic equation. So there might be some other nonlinear transcendental equation. For example, f of x equal to ln x. We cannot represent this equation f of x equal to ln x in the form of equation 1, and that's why these equations are nonlinear equations. So nonlinear equations are another kind of problems that we might need to find out the roots of these equations. So a system of nonlinear equation can be expressed as something like this. F1 of x1, x2, xn equal to 0, f2, then dot 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 fn. So all of these functions, f1, f2 up to fn, all of these functions are nonlinear functions. So this is a system of nonlinear functions. So there are many roots possible for this nonlinear system, and we will see how we are going to find out those roots. So this system of nonlinear equations, we are not introducing any new method. Rather, we can use the bisection method, false position method, or the Newton-Raphson method, second method. Also, we have the QIM method, IQIM method, or simple fixed point iteration methods. So all of these methods can be used for a system of nonlinear equations. So there are no new methods that we are going to learn for solving a system of equation. So this is your home study. We are providing a supplementary document that shows how we can use these methods, these open methods or bracketing methods, for solving a nonlinear system of equation. So that is your home study. In this lesson, we have learned about some scenarios that multiple root might happen. We have learned that the Newton-Raphson method and the second method can be modified for the purpose of multiple roots. So we have also seen that a nonlinear system of equation can be solved using our known approaches. So please try out the MATLAB course for multiple root version, the modified Newton-Raphson and the second method. Please try out these two methods and try to examine how these two methods differ from the traditional Newton-Raphson and second methods. So that's your home task. Please try out those MATLAB course. In the next lesson, we are going to find out how polynomial equations can be used for finding roots. So till then, thank you so much.